In this video, I want to give some basic properties of probability density functions, as well as start to look at how to use them. Since the area under the curve of these probability density functions give me the probability that x is between two particular values, translating that to math, we get that the probability that a is less than x is less than b, so the probability that my value is between a and b, is equal to the integral from a to b of f of x dx. Since the integral of the probability distribution, the probability density function, will give me my area under the curve. We also have that the integral from minus infinity to infinity of my probability density function, f of x dx, is equal to 1. The entire area under the curve has to be equal to 1, since the area of the entire sample space has to be equal to 1. If we consider the uniform distribution between 0 and 1, we have that our PDF is equal to 0 for x smaller than 0, 1 when x is between 0 and 1, and then 0 again when x is bigger than 1. Since we're only looking between the intervals 0 to 1, this is an impossible case. We cannot have values smaller than 0. We also cannot have values bigger than 1, so the fact that both of these are 0 makes sense. We can also see that if we integrate between 0 and 1 of 1, well, the integral of 1 is x, between 0 and 1 is equal to 1. So we do have the idea that the entire integral, the entire area under the curve, is equal to 1, which was one of our main properties of a probability density function. In addition, if we look at the integral from two random variables a to b, well, this will be b minus a. And this is the length of the interval a to b, which is exactly what we said was probability. So this is the probability that a is less than or equal to x is less than or equal to b. So this is the valid probability density function. Let's look at a couple more properties of the PDF. Let's consider a continuous random variable. The PDF is denoted by lowercase f, and the CDF is denoted by capital F. The first property, the probability that a is less than x is less than b. Well, this is the exact same thing as the probability of a less than or equal to x, less than or equal to b, since the probability at any particular point is 0, which is capital F of b minus capital F of a. So this part we discussed before. Whenever we discussed a CDF, we talked about why this particular part was true. So the probability can also be given by the CDF. My CDF can be determined from the PDF by integrating from negative infinity to x. We integrate f of y dy, and this gives us the CDF from the PDF. We can also go the other way. If we have our CDF, we can get our PDF by taking the derivative. So these do have a relationship. The cumulative density function is just the integral of the probability density function. This time, let's consider the uniform distribution from a to b. So instead of from 0 to 1, we're going to pick any random interval. In this case, the PDF is given by 0 if x is less than a, 1 over b minus a if x is between a and b, and it's 0 if x is greater than b. So this here is my PDF, and I want to find the CDF. The CDF is going to, once again, be a piecewise function. The first piece of this, the integral of 0 is just 0. For the next piece, we are going to need the integral from a to x of 1 over b minus a dy. Well, this integral is going to be y over b minus a, since b minus a is just a constant, taken between a and x. So x over b minus a minus a over b minus a. So this piece here, x minus a over b minus a. If a is less than or equal to x is less than or equal to b. For this piece here, we need to consider everything that comes before it, so the entire integral from a to b. In this case, since we've already integrated this, all we have to do is change the x to a b. We get b minus a over b minus a, which is 1, if x is greater than b. So this is my CDF. If the lifetime t, measured in hours, of a randomly selected electrical component has a PDF of f of t equal to 0 for t less than 0, and f of t equal to 0.001 e to the negative 0.001 t for t greater than or equal to 0, I want to find the probability that the component will last between 900 and 1200 hours. Since this is a PDF, we need to integrate. We want this integral to go between 900 and 1200 of 0.001 e to the negative 0.001 t dt. Well, the integral of this is going to be negative e to the negative 0.001 t taken between 900 and 1200. So that tells me negative e to the negative 1.2 minus negative e to the negative 0.9, which works out to be 0.105. So the probability that this component will last between 900 and 1200 hours is 0.105. For my next example, let's let X denote the amount of time a statistics reference book on a 2-hour reserve in the library is checked out by a randomly selected student. And here I have the PDF of this particular random variable. For books returned after 2 hours, students are charged a fine of $2 plus $1 for each 15-minute delay. And I want to find the probability that a student is checking out a book will be charged a fine. So anything after 2 hours. So I want to integrate between 2 and 3, since that's where this piece ends. And I would need to integrate 1 over ln 4 times 1 over 1 plus x dx. And I would want to add in the integral from 3 to infinity. However, that part is just 0, so it's not really going to matter since this whole thing is just going to be 0. If I integrate this, I get 1 over ln of 4 times ln of 1 plus x, going between 2 and 3. So 1 over ln of 4 times ln 4 minus ln 3. And this works out to be approximately 0.2075. So the probability that a student checking out a book will be charged a fine is 0.2075. Next, given that a student has been charged a fine, what is the probability that the fine is at least $3? So we want the probability that the fine is at least $3, so 3 or more, given that there was a fine in the first place. Conditional probability says we want the probability of both, so there needs to be a fine and it needs to be at least 3. And so that's just going to be at least $3. Divided by the probability of the thing I know, the probability that there was a fine in the first place. So let's start with this top. To be an actual fine, well, we need $2 for it to be returned after 2 hours and $1 for each 15-minute delay. So it needs to be returned after 2 hours and 15 minutes. So that's going to be 2.25 to 3. My function was 1 over ln of 4 times 1 over 1 plus x dx. So this is 1 over ln of 4 times ln of 1 plus x, taken between 2.25 and 3, which ends up being 1 over ln of 4 times ln of 4 minus ln of 3.25, which works out to approximately 0.1498. So the top of this fraction is 0.1498. The bottom, the probability of getting a fine, is what we looked at in the last example. We got 0.2075. Simplifying, we get 0.722. So the probability that their fine was at least $3 if we know they got a fine is 0.722.